Hello everybody, welcome to a pre-AP geometry video. Today we're taking a look at Unit 3B, Lesson 2, which is all about proving that two triangles are congruent. So, I want to start off by giving a couple of definitions here that might help us. Starting off with something called the base angles theorem. When we talk about something called the base angles theorem, we really need to understand what base angles are. So I'm going to draw you a little example here. Let's draw a triangle, and let's make sure that at least two of the sides are congruent. I'm going to have these two sides be marked as congruent. We learned last class that this is an isosceles triangle. So, in an isosceles triangle, we end up having these two congruent sides. We call these the legs. The side that is not congruent is called the base, and the two angles that are touching the base are the base angles. And here's a fact about isosceles triangles: they're symmetrical. In an isosceles triangle, the angles opposite the congruent sides are also congruent. So these two bottom angles are going to be the exact same. Similarly, we have a converse of the base angles theorem, which, as you know, is an opposite. If the two base angles of a triangle are congruent, well, then we know that the triangle is an isosceles triangle, meaning the sides have to be congruent. It's the exact opposite of this. With these two definitions, we can put together two corollaries. And as a reminder, a corollary is just a theorem that's correlated with another theorem. So it's based off of the previous two. The corollary to the base angles theorem is this. If you have a triangle, and you know that triangle has all three sides congruent, well, we know that that's equilateral. So there we go. But wait a second. If all these legs are congruent, and the angles opposite the legs are supposed to be congruent, then not only would these two angles be congruent, but if we looked at, let's say, these two legs here and here, these base angles would also be congruent. So all three angles are congruent, making the triangle equiangular as well. So if a triangle is equilateral, then it's also equiangular. And we learned from last class that all of these angles here are going to be 60 degrees. The corollary of the converse is taking this converse and applying it to equilateral triangles as well. The converse talks about the angles being congruent, so the corollary talks about the angles being congruent. If a triangle is equiangular, then it's also equilateral. Perfect. Let's actually use the base angles theorem a little bit here. I'm going to zoom out slightly. There we go. So, a triangle is isosceles, as we know, when it has at least two congruent sides. When an isosceles triangle has exactly two congruent sides, those are the legs. And the angle that is formed by the legs is called the vertex. So it's the very tip of the isosceles triangle. This angle here would be the vertex angle, or just the vertex. The third side is the base, and we know that we call the angles touching the base angles. So let's use this diagram down here and do a little bit of math. If AE is congruent to DE, let's see what we can conclude. Well, if AE is congruent to ED, then we're talking about this big isosceles triangle. The triangle that goes from A to E to D. If those two legs are the same, then we know that its base angles, A and D, are congruent. But what if AB and EB are congruent? Let's look at what that looks like. AB is this small leg here, and EB is this small leg here. So we need to think about what triangle this correlates to. This triangle is triangle AEB. Well, if we simply turn the page, it's a little bit easier to see that these are the two legs and these are the base angles. So we know that we can call that angle angle A, but as a reminder, angle E could refer to a lot of different things. Angle E could be the entire big angle, or we could be talking about this angle, or this angle, or this angle. If multiple angles share the same point, you have to use 3 letters to give it a name instead. So if we want to talk about this angle right here very specifically, we need to use the 3 letters that make up that angle. A, E, B would be one way to name it. With this in mind, I want you to try out C and D and check your answers here in just a moment. So pause the video and see what you get. Hopefully you've had a moment to pause the video and try it out for yourself. So if D and CED are the same, that's referring to these 2 angles. We know that these 2 sides must be the legs. So CE is congruent to CD. Similarly, if EBC is congruent to ECB, this one down here, then these 2 sides must be congruent. It's EB and EC that are the same. Perfect. Let's take a look at the next page and see what we can do here. So these types of problems, when you have 2 triangles combined in this sort of manner, is probably one of the most difficult problems we'll see today. But once you learn the tricks about it, you can apply them to almost any problem that looks like this. So we're asked to solve for x and y in these diagrams. Right away, we identify an equiangular triangle. So, according to the corollary of the converse of the base angles theorem, we know that this must also be equilateral, meaning all these sides are congruent. And we can use that to solve for y. If this side is 4 and this side is y, and y and 4 are supposed to be congruent, then their measures must be equal. Y equals 4. But now here's the trick. This triangle down here has its base angles looking the same. So we know that this triangle is isosceles, meaning if this side has 1 tick mark, then this side must have 1 tick mark. It turns out that all the sides that have 1 tick mark are congruent. So this 4 and this x plus 1 are the same. 4 equals x plus 1, meaning x should equal 3. I'd like you to use this knowledge to pause the video and try out the next one. How'd you do? Hopefully we were able to find that y equals 4 and x equals 7. Again, because according to the corollary of the converse of the base angles theorem, all of these sides have to be the same. And according to the converse of the base angles theorem, these 2 sides must be the same. So all these expressions are equal. You may have noticed while doing that last problem that we have a pretty gnarly looking proof ahead of us. This proof is long, but it's not necessarily difficult. There's a reason why I put this proof in our notes today. The reason is this. Some of us have some trouble with the in-between steps of proofs. The little things, like using the definition of congruence to switch from equals to congruent symbols, or using substitution and transitive property properly. This proof is here to practice those skills. If you want to try this on your own, you may. Your goal is to hit 9 through 11 steps. If you can do this proof in 9, 10, or 11 steps, you've probably hit every little bit that you need to. So if you want to try it for yourself, you can pause, but I'm also going to go through it here. To start off, we are told that the two legs of this triangle, are congruent, that AB is congruent to AC, and we're actually told that the measure of angle A is 60 degrees. These are the things that we are given. In order to solve this proof, we need to show that ABC is an equilateral triangle. So we need to find that that third side is the same. But we don't have any theorems about the third side of an isosceles triangle. So let's think about what we really need to prove here. Because we don't have any theorems about the third side of an isosceles triangle, this triangle should try to be equiangular. After all, if all the angles are the same, then wouldn't all the sides have to be the same for the same reason that we were able to use in these problems? So that's our goal, is to prove that all the angles are the same. And some of us might have a couple ideas on how to do so. So here we go. The first thing that we notice is that AB and AC are congruent. We know that this must make this an isosceles triangle. So, on an isosceles triangle, we can use the base angles theorem. The base angles theorem says if a triangle is isosceles, then we know that its two base angles are the same. And I mean, I'm not going to do this for any particular reason, but I am going to write C is congruent to B, just so we can practice some other skills later. You'll see why, but you could have done B and C. This is the base angles theorem. Okay, so just because those two angles are congruent doesn't mean that they're also 60 degrees. Remember, our goal is to prove that all these angles are the same. But we do have a way to do this. We can use the definition of congruence to change these into equal signs. Why would we want to do that? Because this angle has a number in it, 60 degrees. If you're trying to prove that all these angles are 60, you're going to also have to prove that these angles are equal to 60, not just that they're congruent. So anytime you see an equal sign in a problem, you know you want to switch. We can use the triangle sum theorem to help us solve this problem. The triangle sum theorem says that all triangles have to add up to 180 degrees. So let's write out an expression for this triangle with the variables we know. We know that the measure of angle A plus the measure of angle B plus the measure of angle C equals 180 degrees. And we also know that we can substitute some of these values here. For instance, we know that we can substitute 60 for the measure of angle A because that was given to us. So 60 plus the measure of angle B plus the measure of angle C is 180 degrees. That's just due to the substitution property of equality. But we can go even further than that. Instead of just substituting in the 60 degrees, is there something else we can substitute in? Well, since we know that the measure of angle C equals the measure of angle B, instead of writing 60 plus the measure of angle B plus the measure of angle C, we can just write the measure of angle B twice. Whenever you have two of the same thing in a problem, for instance, if these were both x's, you would just call it 2x, we can combine them. We don't need an extra step to do that. Though if you did want to use an extra step, you could call it a simplify step. So instead, I'm just going to write right away that these will equal 2b, or 2 times the measure of angle b. I also want to subtract 60 from both sides using the subtraction property of equality. This is why your proof could be up to 11 steps instead of 9. It's because you might take an extra step to do these things, but I'm combining them. I subtract 60 from both sides, so I get 120 degrees. And I'm combining these two measure of angle b's to make 2 times the measure of angle b. I think we know how to solve for the measure of angle b now. It's by dividing both sides by 2. So these old properties keep on coming up. The division property of equality lets us divide both sides by 2. So the measure of angle b equals 60. And by the transitive property, if the measure of angle C equals the measure of angle B, and the measure of angle B equals 60, then the measure of angle C equals 60. If you had a different order for this step here, if you wrote down that the measure of angle B is equal to the measure of angle C, it'd be substitution instead. But both would work. This is the transitive property of equality. Now, we know that this triangle must be equiangular. So, by the definition here of what it means to be, not by the definition, because we know that this triangle is equiangular, all the angles are listed as 60 degrees, we can use the corollary of the converse of the base, I'm running out of room here, angles theorem. That's the long one. That's the one that says if all the angles are the same, then all the sides are the same. So triangle ABC must be an equilateral triangle. That is why we have such a long proof here. It's because of all these in-between steps. But the proof itself just wanted us to show that all the angles are the same. Very nice. All right, we're going to move on, and we're going to talk about something called SAS. The question is, what can you conclude about two triangles when you know two pairs of corresponding sides and the corresponding angles are congruent? Let's actually draw these two triangles out. So I'm going to draw two triangles that look identical. In fact, they're going to look so identical that we have a congruent symbol here. I want to mark off a pair of sides that are congruent, another pair of sides that are congruent, and the included angle. When we talk about an included angle is just an angle that's in between two sides. So these angles right here. The side angle side congruence theorem says that if this is the case, if you're able to show that two sides and the angle between them are congruent, then the triangles are congruent. SAS is the order of information you need to know. So you might recall that last class we mentioned we needed to know 6 things to show triangles are congruent. 3 sides and 3 angles. I'm telling you now that we only need to know 3 things. 2 sides and 1 angle, as long as the angle is included or between them. So let's take a look at the next page and see how we can use this. To use the side angle side congruence theorem, remember that in this unit, all of our proofs are basically checklists. We're trying to prove 2 triangles are congruent. You have to basically fill out a checklist. The included angle, like we mentioned before, refers to the angle caught between 2 congruent sides. And the order of the statement, side, angle, side, means the congruent parts must be in this order for the triangles to be congruent. I always joke around and say, can you imagine the horror at naming a theorem based off an angle, a side, and another side? The naming convention would be so bad, there is no such thing as that theorem. So, for example 4, we have to write a proof using the side angle side congruence theorem. And we're given a lot of information. We're given that BC is congruent to DA, and we're also given that BC is parallel to DA. Remember that these are 2 different things. Just because things are parallel doesn't mean they're congruent. In this case, they are, though. We're told that both those are true. And we have to prove that these 2 triangles, ABC and CDA, the ones that are right next to each other here, are congruent. So, how can we do that? Well, we know that one side is congruent. Is there a way of showing that this other side here, side AC, is congruent? I think there is. Remember, the reflexive property says that if a side is shared by two triangles, then it's congruent. Anything is congruent to itself. So we can absolutely say that AC is congruent to, just be careful. The order of the letters is dependent on your proof statement. So A is the first letter and C is the last letter in our proof statement. C is the first letter and A is the last letter in the second part of that statement. So we have to match them. AC is congruent to CA by the reflexive property of segment congruence. Whoops. My congruent symbol kind of went across those pages there, but you get the idea. Segment congruence. We have two sides that are congruent. If the angles between these two sides are congruent, then we know that the triangles are congruent. So if we can show this angle, BCA, as I'll call it, is congruent to this angle, again, B is congruent to D, C is congruent to A is congruent to C, so that angle would be called DAC, then we're good. Then we'll be able to show side angle side. Why would these two angles be congruent, though? That's the tricky part. It might help if I extend out these sides a little bit more, and we might recognize something from semester 1. What I see here is two parallel lines cutting through, or cut through by a transversal. Whenever you have two parallel lines cut by a transversal, we start thinking of alternate interior, alternate exterior, corresponding and consecutive interior angles. In this case, these are alternate interior angles because they're on the inside of the inside of the parallel lines and on opposite sides of the transversal. So by the alternate interior angles theorem, we know that these two angles are the same. So we can prove using SAS that these two triangles are the same. And we're good to go. I want you to try example 5 on your own. It uses a lot of the similar information, but this time we're also talking about perpendicular lines. So pause the video and give it a shot. Hopefully you've had a chance to try it out. First of all, if we know that RP is perpendicular to QS and PQ is congruent to PS, we know that those are our givens. We can use the SAS congruence theorem to show that these two triangles are the same. And the way we do it is this. First off, this angle right here and this angle right here should be the same. But it takes 2 steps to prove it, not just one. Because we want to show that this angle right here is a right angle. Angle RPQ and angle RPS, again, I got these letters from the congruence statement, are right angles. That's the first thing that we're trying to show here. And we know that's true because they're perpendicular. Whenever two lines are perpendicular, it creates all right angles at that intersection. So that's the definition of what it means to be perpendicular. Two lines are perpendicular if they form right angles. But we also know that all right angles are the same. This is actually something that we proved back in Unit 2. All right angles are congruent because of the right angle congruence theorem. That's the one that says if you have any right angles, they're all going to be the same. All we need now is to find a missing side that the angles are in between. And I think we've got our candidate right here. Side RP needs to be the same as side, well, RP. RP has to be congruent to itself. Again, you can look at the letters up here to see that P matches with P and R matches with R. It's congruent to itself because of the reflexive property. Told y'all we'd be using this quite a bit in this unit. reflexive property of segment congruence. And then we can just use SAS once again to show that these two triangles are the same. Triangle PQR is the same as triangle PSR. Fantastic. So SAS is a really good tool for us to have. It shortens the amount of things we need to prove down to 3. Just 2 sides and the angle between them. I'm going to teach you 2 more shortcuts here as well. These 2 congruence theorems are just 2 other shortcuts, so you don't need to prove 6 different things about a triangle just to show they're the same. So let's take a look at these. Starting with the side-side-side congruence theorem, or SSS. If you have 2 triangles, and you know that all their sides are the same length, well, think about it. If their sides are the same length, that means their angles are positioned between the sides. If one side suddenly got longer or shorter, the angle would get smaller or larger. So when all the sides are the same, all the angles are also the same. In other words, if you can show that 3 sides are congruent, then the triangles are congruent. This last theorem we're going to be learning today is called the hypotenuse-leg congruence theorem. And it's important to remember what a hypotenuse is, because some triangles don't have one. A hypotenuse is the longest side of a right triangle specifically. This is your hypotenuse. It's the one across from the right angle. And this is your leg. So, as long as you can show the hypotenuse of 2 right triangles are the same, and either one of the legs of those right triangles are the same, then you've got hypotenuse-leg congruence. So let's draw these 2 right triangles, here and here. And the rule is, if these are both right triangles, if their hypotenuses are the same, and one of the legs are the same, then they are congruent. So it looks like it's a 2-item checklist because it looks like you just need the hypotenuse and the leg. In fact, let me write that down. We need the hypotenuse. We need to prove that one of the legs are congruent. But because we actually need to have a hypotenuse in the first place, we also need to prove that it's a right triangle. So there's actually still 3 things we need to prove, even though it looks like 2. Let's talk about these. So far, we can prove that 2 triangles are congruent in a couple of different ways. We can prove it if corresponding sides and angles are congruent, or if a side, angle, and side are congruent. But like I said, now we're adding 2 more to our toolbox. If all the sides of both triangles are the same, then the 2 triangles are the same. So in our proofs, all we need to do is show that each side has a congruent counterpart. Let's do a really short one here. Let's do a little warm-up proof. If we know that KL and NL are the same, those are those top sides, and KM and NM are the same, those are the bottom 2 sides, can we prove that the triangles are the same? Absolutely, because all we need to do is show that the third side is the same. And because this third side is shared by both triangles, we know that we can use the reflexive property. So LM is congruent to, let's check the order of the letters in the statement. LM is congruent to LM by the reflexive property once again. Reflexive property of segment congruence. There we go. So if all 3 sides are the same, we can just say SSS is the reason for these to be congruent. You can write down SSS congruence theorem, but I'm trying to save you some writing here. You can just use the abbreviation. Now let's take a look at a proof like example 7. I actually want you to try example 7, and I want to let you know there's 2 different ways to do this example. So I want you to pause the video, see what you can do with this example here, and we'll be able to talk about one way to do it. Pause the video for example 7 and see what you can do. So hopefully you've had a chance to try this one out. This really hinges on us knowing what bisect means. And no matter what proof style you use for this, we need to use the definition of bisect, or the definition of a bisector. Bisect means to cut in half. So if QS is bisecting PR, then each half of PR has to be the same. No matter which proof style you use, you're going to want to show that PS is congruent to, let me check the statement here, RS. One way to do this proof, folks, is to recognize that this is an isosceles triangle. If a triangle is isosceles, then we know that its base angles are the same. You could use side angle side for this. But I bet that most of you were able to recognize more easily the reflexive property here with QS. We know that QS has to be congruent to, again we check, and it should be QS, by the reflexive property of segment congruence, and we're able to show that these 2 triangles are the same for that reason. Last but not least, we have the hypotenuse leg theorem. This one's tricky because it requires a right triangle or a right angle to work. Because by the definition of a right triangle, if you have a right angle, it's a right triangle. Once again, recall the hypotenuse of the right triangle is the longest length, and a leg is just a different one of the sides. As we sort of implied before, SSA congruence does not work in any other circumstance. This is the one theorem that does not work. After all, like I said before, think of the absolute horror of naming it if you had to name it backwards. So instead, let's take a look at our given here. We're told that WY is the same as XZ. WY is this long diagonal here, and XZ is this long diagonal here. We're also told a couple of perpendicular segments. So WZ is perpendicular to ZY. That's this part right here. And XY is perpendicular to ZY, which is this part right here. This diagram is very confusing because the triangles have some overlap. So here's a hint to help you if the diagram is a little bit rough or confusing. I recommend redrawing the diagram as 2 separate triangles if there's too many parts to keep track of. The only tough thing with drawing it like this is you don't see what line segments are shared by the triangles. So we just have to keep in mind that line segment ZY here is on both triangles, so that's a shared line segment. I want you to pause the video and try this proof out because I think it's going to be a useful one to at least see how it's done, to try some of the steps, maybe not do it 100% correct, because when we talk about it, I think we'll see a lot of aha moments. Pause the video and see what we can do. So, we need to use this definition of perpendicular lines. By the definition of what it means to be perpendicular, it means we have some right angles here. So we know that angle WZY, again we need to use 3 letters because there's 2 angles on point Z, and angle XZY are right angles. That's what it means to be perpendicular, is that it makes right angles. So these 2 angles are right angles, or if you want to look at it in the big diagram, there we go. Okay, this this is actually going to be pretty important for us here. In fact, I think we actually might need, yeah, we really do need an extra step here. So I do apologize, folks, for taking that extra step off. If you did it in 4 steps, fine for this one, but we are missing a tiny little in-between step. The in-between step is this. We need to show these are right triangles in order to show that we can use hypotenuse leg. So we actually do need to say that triangle WYZ and triangle XZY are right triangles just by the definition of what a right triangle is. Again, if you skip this step in between, don't worry, our answer key also skipped it in between. To finish the proof, we know that the hypotenuses of both these triangles are the same because it was in our given. We just need to find one leg that's the same. And we get to use our good old faithful reflexive property for that because ZY is shared by both triangles. So we can say that ZY is congruent to YZ by the reflexive property of segment congruence. Which means, using hypotenuse leg, we've shown it's a right triangle, and we've shown the hypotenuse and the leg are the same. We know that these two triangles are the same. I hope, folks, that these proofs that we did in this section have really helped us to get some practice with each individual step. We'll be talking about them more next class with some extra shortcuts. But for now, have a fantastic rest of your day.